So there is a question by M. Rekha. So why O is not incorporated as a VI element? Sorry, I don't understand the question. If you could type this again clearly, I don't know why. Oh, okay, I understand. This is pertaining to the periodic table. Why is an oxide not being considered as a group 6 element? Sorry, yeah, oxygen, polonium. Some of these are snipped out of the series. The main reason why oxygen is not considered, oxides are intrinsically a bit different from the other chalcogenides. They have their own problems with defects and slightly different properties. Indeed, many of the 136 analogues of oxides do exist, but by and large, it is more convention, and this difference between electronegativities and softness of oxygen and the other chalcogenides, why the oxides behave a bit differently. So they don't come properly within that. Then the next question is, is one of the spectra, there was a subsidiary P. Please explain. Sorry, if you could, this is from Amit Kumar Pathak. If you could clarify which PL spectrum it was, I'll just presume that this pertained to the device PL spectrum, perhaps. Was it this one? I'll answer with respect to this one. In this case, this is not a luminescence peak, but rather this is the peak of the excitation which we have used. In this case, we are using, this is directly emission coming from the device, and this is actually the LED emission spectrum, and this part is the device's PL spectrum. So now the question from Gaurav Gupta: what is the condition to synthesize copper aluminum sulfide, Cad sulfide type nanocrystal, and can he use lead sulfide in place of cadmium sulfide? There are some issues. So firstly, copper aluminum sulfide, Cad sulfide, I mean, it's made again via standard colloidal synthesis. The incorporation of lead sulfide instead of cadmium sulfide will be quite challenging. There are a few challenges in growing lead sulfide. It's not clear whether it goes straight or whether you use an anion exchange at some step to do it. So that is one issue. The second issue, which is a more major issue, is the rock salt-like structure, and copper aluminum sulfide is quite a bit different. It's a tetragonal chalcopyrite, and there are again massive differences in the softness of lead compared to aluminium. So all in all, it could be challenging. I'm not sure if you can replace cadmium sulfide with lead sulfide. It would be an interesting exercise if you can, certainly worth it, but I'm not sure if it can be done that readily. So not a question which I can answer because we have not tried it. Now, then there is a question from Amiya Kumar Panda. One of the main issues in nanoparticle synthesis includes the reproducibility in maintaining the shape and size. Absolutely. Each and every time, most of the researchers experience the formation of nanoparticles with different size and shape. How is it possible to maintain consistency in size and shape of nanoparticle during its synthesis? So the answer is, I mean, as you have already stated, you require a large amount of experience during the synthesis, and you do need to tune the conditions very, very carefully in order to do that. So in a sense, the answer is itself the question. So, clearly if you use one generic set of conditions, it's not possible to have monodispersed nanoparticles all the time. You really have to optimize your conditions, and then things go as you may wish to. I hope that answers the question. Now, moving onward, I have something from anonymous attendee. By what factors we can call copper iron sulfide make quantum dots, and what are the measurements to prove this will? Okay, by what factors can we call the copper iron sulfide made quantum dot? So you're basically asking how was copper iron sulfide nanoparticle characterized? Well, the answer is, through multiple techniques. You can look at its, chemical formula, that it is indeed copper, iron, and sulfur containing. You can examine its other properties, which include its X-ray diffraction, its surface structures using XPS, and so on. And all of that was done by us. So, you cannot prove that anything will form quantum dots per se or nanocrystals per se, but rather you can make a nanocrystal, then check whether it is copper iron sulfide or not. What I'll add here is that we call, again, there's a slight trick here, and I'll admit to it, which is that when we say copper iron sulfide, we mean a structure which has copper, iron, and sulfur in it, but invariably in nanocrystals, these stoichiometric trees of copper, iron, and sulfur are seldom exact, and this is a very well-known thing. So when you're making a nanocrystal, your exact chemical formula of the nanocrystal will be slightly different from Cu1, Fe1, S2. It will differ. And in fact, we find wide variations there depending on the size of the nanoparticle and the ligands which are used. Now, the question next one is, can we use zinc sulfide in the place of cadmium sulfide? Absolutely, that is the main trick which is important, and that is what has to be done largely. Zinc sulfide is a good substitute for cadmium sulfide, but then there are problems. Zinc does not quite have the same passivation ability as cadmium sulfide. Now, in this case, for example, and there is some change in the properties. So, for example, take the case of copper aluminum sulfide. In the case of copper aluminum sulfide and cadmium sulfide, we are getting one behavior. We are having a large Stokes shift. We are getting emission. If we made copper aluminum sulfide zinc sulfide, we find that this is a system which actually expels its electrons to the nanocrystal surface, and this leads to photocatalytic behavior. So, zinc sulfide is not a tool to be used directly as a direct substitute for cadmium. It's a good angle of investigation, but it does not always work. To give another example in not always working, the idea for zinc sulfide would be that if you look at copper iron sulfide, it's actually not possible to grow zinc sulfide cleanly on copper iron sulfide. Most of the time you don't get it. So those are tricks to be figured out. But yeah, it's definitely a good candidate material. So now, now this is a question from Sovic Kiri. How does one measure the quantum confinement? I might have a slide showing that. Let me quickly try to address that question. Well, the quantum confinement is measured basically depending on how far away you go compared to the band gap of the substance. So to explain that, let me just go to a different slide altogether. Yeah, this one. So what we have here is, you see that as I make the nanocrystal size smaller, the band gap changes, and this can be used to measure as a metric for quantum confinement. And if we fit it with, a graph which suggests, quantum confinement, then in that case we find also what the reduced effective mass of the system might be. So it's basically measured as a shift in terms of the band gap with respect to the size of the nanoparticle. That's the most convenient way to measure it for pure materials. For materials with their core shell structures, you may have the issue of alloying, in which case the entire picture gets a bit muddied up. And that is the case in 136s. A lot of the shifts actually happen because your composition changes rather than the size. So after that, there's a question from Harsh. Could you please inform, can the nanocrystal be designed to emit from triplet states? So Harsh, so I think the question, you might be coming from an organic chemistry background. So indeed, nanocrystals we don't have to worry about that as a consideration, firstly, because the singlet triplet splittings of nanocrystals invariably are a lot smaller. In the case of the context of nanocrystals, these are termed as bright and dark excitons. The splittings between them are extremely small, and usually spin flips, which are very uncommon. They're called, intersystem crossings for organics. These would be very, very common and convenient to attempt in quantum dots. So we can have, triplet states actively coupled to singlet levels, if you will, just by using thermal energy, and that's not much of an issue for nanocrystals. At very low temperatures, indeed, you can find that the dark exciton materials like cadmium selenide does start dominating a bit, but not at room temperatures. Then there's one more question from Harsh. He has a question, are these nanocrystals stable enough for practical applications? Absolutely, because I've already shown you copper, aluminum sulfide, zinc sulfide, right? That's a material which is doing so much work. It's converting carbon dioxide into, fuel. So it's doing it actively with sunlight. So these are quite a bit very stable. And 136s in particular are extremely, extremely stable. So not an issue per se, if you have the right formulation at hand. Now, what about the selenides? Indeed, a great question. This is from Bala Subramaniam. I have actively tried to avoid the selenides in this presentation. We have investigated a few. For example, copper iron diselenide is something which we continue to investigate. We avoided it for these applications because I was trying to stick to elements which are 30 or less in this presentation. So copper, aluminum, copper, iron, sulfide are about the only two I picked. It is possible to make the selenides. We ourselves have investigated a few. A lot of the photovoltaics, successful photovoltaics, do use copper, copper, aluminum, copper, indium, gallium selenide. It's a very, very successful photovoltaic material. So those do exist, and selenides are very interesting from the 136 family. Certainly, no questions there. We have just not covered them in this presentation. Now, there's a question from Dr. S. Manivandan. Is there any charge transfer possible? Absolutely. There is definitely active possibility of having charge transfer in these materials. My favorite example of charge transfer would be coming out of copper, aluminum sulfide, zinc sulfide. It's a material which we are actually, as I said, very, very excited about. That's because it has really fast, essentially an ultra-fast charge transfer, which occurs to the surface. And this allows this material to have extreme photocatalytic activity. This material actually transfers its electrons to the surface in barely 560 or thereabouts femtoseconds. I don't know, materials which can transfer any faster. And so charge transfer is indeed possible. That is something which you want to exploit, perhaps for things which you are using for photovoltaics, perhaps for things which you are using as photocatalysts. But it might not be something you wish to exploit for, say, emissive substances. If you're trying to have luminescence as a targeted application, then this is a little undesirable to have charge transfer, but definitely it can be engineered, and that's the beauty of the nanocrystals. So great question. Then there's a question from Somnath Das. How quantum confinement can be achieved here? By varying temperature or by varying precursor concentration of ligands. So I presume that you're talking about, again, the synthesis conditions. How can we make smaller nanocrystals and get quantum confinement in them? Well, the answer is a bit of both. You can, if you, depending on how you play with temperature, if the injection is done at a very high temperature, carrying on growth at low temperatures is one way to growing smaller nanocrystals. Again, if you are, however, using a continuous steady heating strategy, then that does not work out so well. If you're varying precursor concentrations or ligands, certainly by having longer ligands, or else by having lower precursor concentrations during growth, but not during nucleation, high during nucleation and low during growth, one can actually achieve regulations size and get quantum confined nanocrystals. So it's possible, but for the most part, as soon as you cross some size threshold, like 5 or 6 nanometers for materials, which are not that large, you immediately are no longer having significant quantum confinement. That's what I meant to say when I said in the very beginning that I would be focusing much on quantum confinement here. Does the surface polarons interact with each other or other electrons? So I presume you mean surface plasmons of this material. Yes, there is an interaction. Now, I'm not sure what the question is, but I'll try to interpret. So going back to the experiment which I had described, I guess I've crossed it. I think it's right here. Yeah. So going back to this particular experiment, I said that we have used sparse films of copper, iron, sulfide nanocrystal. There's a good reason to use a sparse film. Sparse means that the nanocrystals are far apart from each other, and if they move very close to each other, we see that they couple, and there is a strong redshift of this plasmonic feature. So it is very sensitive to its environment, and even other nanocrystals count. So their coupling itself shifts this. So that's definitely happening here, and that's why we investigated sparser films. So how to deal with the toxic? So there's a question from Gopal Kulkarni: how to deal with the toxicity of cadmium sulfide? Is there any other replaceable material instead of CDS? Great question. I mean, we keep looking for it. Zinc sulfide, as was mentioned earlier, is a great material, but it's always difficult to get. If you're targeting applications, again, zinc sulfide. Not every material can replace cadmium. Cadmium is great for luminescence. Zinc sulfide a bit harder to use for luminescence. We've done it now. We've succeeded. But it remains an active area which needs to be looked at further. But zinc sulfide is the obvious answer here. There are others, but we haven't had quite as much success with them. So then there's a question by Abhishek Datta: is there any possibility for charge transfer which may be useful for applications? Absolutely, charge. I mean, I keep going back to my favorite slide of seems which is this one right here, where we are showing the behavior of copper aluminum sulfide, zinc sulfide. And indeed, we are able to get a massive photocatalytic efficiency. And I remain hopeful that maybe in a few years' time, this would be used to actually significantly blend fuel. And I think it's very easy and very doable, and we are hopeful of doing it. So I've run out of questions in my Q&A dialogue. Let me see if there is more. If I reopen, no. I think I've addressed all the questions in the Q&A dialogue, but now there is something in the chat box. So let me look there. Yeah, I think there's no further questions, right?
Yes, Professor Pandey, there is one question in the chat box. Is
I see.
CuFES2 or 2D, something like that, from Keval Bharti?
It's not at all a 2D material. It's a proper three-dimensional lattice structure. Yeah, it's not a 2D material.
So I think you have covered almost every question into the Q&A tab, and
Sure.
I think there are no more questions from the audience. So,
yeah.
So let me thank you, Professor Pandey, for the exciting and illustrative talk. The lecture must have inspired many young
Thanks a lot
to think and define new problems in this particular area.
So thank you.
Yeah. And you might have seen several messages in the chat box saying thank you and how much they have enjoyed the sessions. Wonderful talk. To update
Thanks a lot for arranging everything.
Yeah, so to update you, we had more than 100 participants in this particular session, and you basically answered all the questions. We'll be posting the recording of this particular session after a few edits on our ACS India page soon. Regarding the participation certificates, we'll be sending it to the attendees. And finally, once again, thank you all for your time and the wonderful participation. We'll be back with another exciting session in the next week. Till then, stay healthy and stay safe. Once again, thank you, Professor Pandey, for taking your time and for your wonderful talk. Thank you very much.
Thank you. Thanks a lot. Thank you.